Yeah, I have a bit of a sketchy voice today, but anyway. And I tried to read a comment before, but it got deleted or it's not available anymore. David, if you would like to post it again or something. Anyway, I don't want to read, I won't read the whole article to you because it's quite long. It's just really interesting, the whole thing, what they're talking about. We had this atmospheric lake recently, mapping a river beneath the sea. A recent expedition mapped one of the world's longest submarine channels, revealing previously undiscovered physical features and raising questions about its unusual origin and shape. It's a really long article. I'll just read a little bit and show you some pictures. Along the sloping margins of most of the world's continents, underwater canyons and channel systems extend from sources on land to sinks in the deep sea. These submarine channels, which share many similarities of form and functions with rivers on land, are critical in Earth's sedimentary and biogeochemical cycles. Geochemical. They not only distribute eroded continental material to the deep sea, but they also redistribute carbon and vital nutrients such as iron, calcium, phosphorus, and sulfur across Earth's surface. Yeah, maybe they come also from beneath and from above, but anyway, I'll leave it here. Yeah, my voice is really sketchy. I won't talk too long. That's the map of one of those rivers they found. And the funny thing is, as far as I understood, there's actually not too much of slope that it would gain in speed like you would expect from water which is pouring down a steep hill. It gets faster than water which is on a really uh, much more horizontal underground. Let's continue here. Comparisons between deep sea channels and river systems are common in the literature. However, there are fundamentally different physical processes at play. The sediment-laden turbidity currents that form subsea channels, such as NAMOC, are aperiodic, and many of their properties, including their downslope velocities, are largely dictated by flow volume and the density contrast between the flow and the ambient fluid, seawater, in addition to the gravitational force acting along the sea floor gradient. As the front portions of turbidity currents are known to hydroplane, the bed substrate seafloor has little bearing on the nature of these flows, which show their highest velocities close to the seabed as a result. In contrast, river flows continuously erode their channels and are dictated entirely by gravity gradients. Channel dimensions, flow volume, and the roughness of the riverbed substrate. The ambient fluid, air, is not a significant factor because the density of air is so low that it does not affect the flow of water. Because of bed friction, river currents are generally fastest toward the top surface of the flow. There are other distinctions, of course, but the conclusion is that all through deep sea channels and rivers have analogous characteristics. These features likely result from different hydraulic and sedimentologic processes. Sedimentologic, maybe. So, let's go to the picture. There's actually a video, just have a quick look at that.
This animation shows a fly-through over part of the Northwest Atlantic Mid-Ocean Channel, or NAMOC, a submarine channel that wends its way for more than 3,800 kilometers from Hudson Strait in the north, through the Labrador Sea, and around the Grand Banks of Newfoundland. The channel is recreated using new multi-beam bathymetric data acquired acquired during Expedition 102.
Okay, I just want to interrupt once quickly because I was thinking about if that's this kind of current flow in the mantle, which makes it so much more dense there. Like, there's really a big current of energy flowing beneath the ground, which excites the water and makes these kind of things even possible. And also the capacitance of the whatever you have, different kind of salt waters, melting waters, and these kind of things. And is there any possibility that there is like fresh water pouring out of the rock there, which is forming this channel, which is somehow so much mineralized that it just stays there, basically magnetically, and moves also magnetically, and not by gravitational forces. But anyway, let's have a quick look at that, and I'll leave it here. And yeah, it really sucks that I cannot see all of the comments because they just disappear. So maybe I have to post them again. Thanks.
Aboard the German research vessel Maria S. Mirian in summer 2021. Shown here is a render of the JEPCO 2021 bathymetric grid of the Labrador Sea with the multibeam data draped over it, looking to the north. The southern tip of Greenland is to the east, and Newfoundland and Labrador are seen to the west. The animation starts just east of the northern tip of Flemish Cap at about 49 degrees north and proceeds northwards to the source region of Naymock, seaward of Hudson Strait, at about 60.5 degrees north. Dark blue colors are deep and reds are shallow. The regional bathymetric gradient of the seafloor, which dips slightly to the south, has been removed with a low-cut filter to colorize the depth of the channel uniformly relative to the levees, so the depth color scale is relative. Pinnacles of red are basement outcrops. Vertical exaggeration is 20 times. For scale, the channel is about 5 kilometers wide at its base and 100 meters deep.
Those red ones are fulgamites.
Note the steep walls and box shape of the channel, as well as its general sinuosity. Also, keep an eye out for depositional patterns along the channel floor. The respective height of the western levee on the left relative to the eastern levee, and multiple tiers in the channel walls in certain places that represent mass failure scarps and erosional terraces. Here you can see a couple of basement outcrops in the red pinnacles. If you look at the channel floor, you can see depositional patterns. You can see a particularly good head scarp below us there now. You can see the width of the channel in this location and a bit of a channel tallweg as it makes its way around this bend, perhaps confined in part by these outcrops. Here the channel broadens and the eastern levee is almost absent. Here you can see on the left one of the few tributaries reaching into Naymock from the western side. Again, notice some of the patterns within the channel floor. You can see the western levee is higher, but you can also see some complexities on the western levee due to mass failures or slumping into the channel. We're approaching now the area.
Yeah, you can watch the whole video. I don't understand I probably know what they mean with mass failures, but it doesn't make any sense. But anyway, probably this underwater river is just, how to put it? It is still at work by transferring energy, and it is even exciting water. So there must be quite much energy flowing in that crack, I guess. And those red ones are fulgamites. Probably they're also volcanoes. Who knows? But anyway, I leave it here. It was an interesting find about submarine channels. Thanks. Bye.